Hello friends, today we will be learning frequency modulation practical from principles of communication system. So first of all we will understand what are the prerequisites required for this practical to understand better and what are the equipments that are needed. So let's start. FM modem. Modem stands for modulation and demodulation. So frequency modulation is a form of angle modulation. In that we are using two signals. First is the modulating signal and second is the carrier signal. Carrier is a high frequency sinusoidal signal whose frequency is modulated or it is changed as per the variations in the amplitude of the modulating signal. Here modulating signal amplitude and phase is constant. The biggest advantage of the FM is that its amplitude always remains constant, making it more immune to noise. This can be particularly useful for mobile applications where changes in location as the vehicle moves can bring about significant signal strength changes. So if a vehicle is moving from one place to another place, the signal strength is changing, means the amplitude of the signal is changing and accordingly the frequency of the signal will change. That is what the frequency modulation is. Now let us say what are the prerequisites required in understanding this practical. So first of all, you should aware of the concept of FM, that is frequency modulation, and FM generation techniques. Objectives here will be to study the blocks in generation of FM. So first we will understand the front panel of the kit that we are using for FM generation. Then we will study the FM waveform in time domain with the application of modulating signal and carrier signal will be generating the FM signal. To study the effect of modulating signal amplitude and frequency on the FM wave and then plot waveforms for modulating signal, carrier and FM modulated wave on the graph paper. So this will be the self practice for drawing the graph on the graph paper. Now what are the apparatus that are required for it? So these are shown here. So first is the kit will be required, that is an Cassionetrica kit, then an DMM, BNC connector called as BNC banana to dual banana male female jack coaxial connector. So these two are the banana connectors that are required and this is the BNC connector. Then and DSO Tektronix TBS 1000C we have used here. You can use any DSO available in your lab. Then connecting wire with banana leads. So these are the wires that are banana leads. Now next, what is the execution? So first we will generate the FM modulation and then we will detect the modulated signal. So we will be performing two operations, frequency modulation and demodulation in the first part. In the second part, it is the modulation index calculation, and the third part, observing the FM spectrum and observing the variations in sidebands with the change in modulating signal. Now, what are the observations that needs to be note down are first is modulating signal frequency and amplitude. So we'll be keeping here the minimum modulating signal frequency and amplitude of 500 millivolt, which are as per the specifications of the kits. Then carrier frequency and amplitude. So we will be keeping the carrier frequency as 50 kilohertz. It is an high frequency sinusoidal signal and amplitude up to 2 volts. Calculations will be frequency deviation will be calculating by observing the two frequencies F2 and F1 with the change in the bias voltage. Modulation index will be calculating from the frequency deviation divided by the modulating frequency. From the modulating index using Bessel's function, number of sidebands in the spectrum of FM can be estimated and observed on the frequency spectrum of FM. So this is the front panel of the kit that will be used for FM modulation. It is divided into two parts. First is the transmitting and another one is the receiving. So the top part here is the transmitting end and this is the receiving end. Here IC8038 is used for the generation of a sinusoidal signal. This is an high frequency signal whose frequency we can change with this frequency adjustment. This IC is basically used in the function generator for generation of various waveforms. Now, what are the signal that is generated from this IC8038? It is an high impedance signal. In order to use it for further processing, and buffer is used. So this buffer is work as an isolation from the signal to the processing operations that are done. This buffer is also used for reducing the impedance so that whenever the signal is used for further processing, there will be no loading effects. So we will be generating the carrier signal. Here you will be able to see the carrier signal at the output of this buffer. This IC8038 with the input of some external signal, it can have the modulation signal generation also. So here we are using this IC8038 for FM generation, that is for frequency modulation. So the another signal given at the input to this IC8038 is the signal generator signal called as the modulating signal, whose frequency can be adjusted using this frequency adjustment knob and the amplitude adjustment knob. So we will be able to connect the output from this signal generator to the input of this IC8038, and here you will be able to observe on the DSO the frequency modulated signal. Another signal that can be adjusted using the same knob is the DC bias of this IC8038. We will see in the practical purpose how we are using the DC bias to find out the modulation index. Next is the receiving part. So here the transmitting, because we are combining modulating signal and carrier signal to observe the frequency modulated signal here. Now we want to detect the modulating signal that we are transferred from the transmitting end. For that purpose, PLL 565 FM detector is used, whose frequency can be adjusted with this knob. The frequency of this PLL 565 should be matched with the carrier frequency in order to extract the detected signal, that is the modulating signal at the output. Now here this output signal may contain the high frequency component. So it is a distorted version of the signal that we are transmitted. So a low pass filter is used here, which will get the input from this PLL 565. So output of this 565 will be connected to the input of this filter, which is a low pass filter, and at the output you will be able to observe the detected signal, that is the modulating signal. Now let's start with the practical, how we can see the frequency modulation and demodulation. So you can see this is the kit. Okay. What are the blocks just now we had seen on the screen? The same are here. So this is an IC8038 which is used for the generation of the carrier signal. The carrier signal you can observe here at the output of this buffer. This is a signal generator which will be generating the modulating signal, whose amplitude and frequency we can adjust with these two knobs. Okay. And this modulating signal will be connected at the input of this IC8038 in order to observe the FM generation at the output of this buffer. Now this is your detector part, that is the receiving end, and here you can see that this is PLL 565 phase lock loop, whose frequency we had to adjust with the carrier frequency. Here we are setting it to 50 kilohertz, and this is a low pass filter which is used for detecting the distorted output detected from the PLL. So high frequency components will be removed from this and you will be able to observe the clear modulating signal at the output of this low pass filter. Now this is the DMM that is used for noting down the DC bias which is applied here at the IC8038, and this is the CRO that we are using to observe the various output and signals. Now let us start with generation of the carrier signal. So I will start this kit. So this is now turned on. Okay. Now this BNC connector will be connecting here at channel 1 of your DSO. Let us connect the ground here to the ground of this kit. So this is the ground, and one terminal that is here at the carrier. Now you will be able to see the carrier signal here that is generated. Now let us see what is the frequency that we have set here. So frequency will be adjusting it to 50 kilohertz. Let's do here the auto set. Now you will be able to see the frequency here. We have set it to 50 kilohertz almost. So this is something 50.78. You can fine tune it with the knob here which is mentioned. So I am setting it to almost 50 kilohertz, which is a carrier of high frequency component. Okay. Now this is the carrier signal. Now let us observe the modulating signal. So we will be connecting CRO input to the signal generator here, and on the CRO now you will be able to observe the modulating signal. So we have to keep the modulating signal frequency at the minimum level. So this frequency we will be keeping at the minimum level. This will be almost in hertz. So it is almost 592 hertz. So after times per division scale, you will be able to see this is the modulating signal. And what is the amplitude here? We are adjusting it to almost 500 millivolts. So this is what we are adjusted to, almost to 500 millivolts. So it is showing to 500 millivolts. So we adjusted this to the 500 millivolts. So this is what our modulating signal. Now let us connect the modulating signal at the input of IC8038. So we will be connecting this modulating signal at the input of IC8038. Okay. And now you will be able to observe the modulated output on the DSO. So let us observe the modulated output on the DSO here. So connect here the output at the buffer, and now you will be able to see the modulated output. So this is the frequency modulated output you will be able to observe on the DSO. Right? So this is frequency modulated waveform. If you want to observe the effect of the amplitude on the frequency, I will be changing the amplitude of the signal generator here, and you will be able to observe the effect on the frequency modulation. So if I am changing the amplitude, it is showing me the effect on the frequency modulated signal. So you can observe this. So this is what your frequency modulated signal. Correct. Now let us move on for the demodulation. So for the demodulation, you will be setting the frequency of the PLL to 50 kilohertz. So we have to match the frequency to 50 kilohertz in order to get the signal detected at the receiving end. Correct? So now this is what it is generating the square wave. You will be able to see the square wave, and somewhat the frequency is high. So with the frequency now, let us adjust the frequency to 50 kilohertz. So this is adjusted to 50 kilohertz. This is a phase lock loop, so we had to lock the frequency to the carrier frequency. So this is 50 kilohertz we adjusted. Now we will be connecting the generated output, that is the FM output, as the input to the phase lock loop, that is PLL. So output of this is your FM output. Let's connect it to the input here. So this is connected to PLL. And let us observe the output at the PLL, whether it is a demodulated signal or not. Now see on the DSO. So this is the distorted version of your modulating signal. Correct? Now we want the detected signal, that is the modulating signal without distortion. So we'll apply the output here. You can see the output of the PLL here will be applied to the input of the low pass filter. So output of the PLL will be applied at the input of low pass filter, and then we'll be connecting the output, that is of low pass filter, to the input of DSO. Now you will be able to observe the perfectly demodulated signal here. So this is what your demodulated signal, and this is nothing but what? Modulating signal that you are applied at the transmitting end, and this is exactly that what you have applied here. So this is what the demodulation part of this. So we had seen the modulation and the demodulation. So this is the demodulated output. Exactly we are getting the same millivolt that you have applied. Now if you are going to change the amplitude of the signal, then it is going to affect its output also. See. So this is how it is changing. Correct? So this is the perfectly demodulated output, almost the same that we have applied here. If you are going to change the frequency also, then it is going to affect on this. See, this is what the perfectly demodulated output. So if you are matching the frequency of the PLL with the carrier, then only you will be able to detect the modulating signal perfectly. Otherwise you will be getting the distortions. So I hope this modulation and demodulation part is clear. Now let's move on further to see how to calculate the modulation index. So for calculation of the modulation index, now we will remove the complete demodulation part here, and we will just see the FM output. So I am removing all this, correct? And here I will be applying the modulating signal at the input, and here you will be observing the modulated output. So this is what you will be able to observe, the modulated output. So this is what the frequency modulated output. You can see this is the frequency modulated output. Now we are to observe what is the DC bias at this point. So in order to observe the DC bias, you have to connect the DMM one input, which is ground, and another to the DC bias input. So you are connected it to the DC bias. So at this point, what is the signal level? It is almost 7.84. Okay. So when your carrier frequency is 7.84, this is nothing but what is the, now in this 7.84, okay, correct. So you have to add zero point 0.5, 7.84 plus zero point 0.5 and 7.84 minus zero point 0.5. So if we are deducting from this 7.84 minus zero point 0.5, it comes out to be almost 7.83. So just change this voltage from the frequency adjustment of this IC8038 to 7.53. This is 7.50. Let's say tentative, we are taking it to 7.5. And what is the frequency at this point? You have to note down the frequency from the DSO. So this is coming almost something 54.54 kilohertz. So note down the frequency, that is 54.54 kilohertz. Okay. Now next you have to add zero point 0.5. So 7.8 plus zero point 0.5. So it comes out to be nearly 8.3. So let's change this to 8.3. So this is 8.3, and you are getting the frequency here, this is 44.28. So you are getting the difference of the two. So subtract the previous frequency from this frequency, you are going to get the delta F, which we have seen in the presentation, and divided by the modulating frequency, you are going to get the modulation index. So if you are increasing or decreasing the frequency, then you will be able to observe the change in the modulation index over there. So this is how you are going to calculate the modulation index, correct. And now let us observe the FFT, that is the frequency domain representation of it. Before that, let us see, if you are calculating the modulation index, then this is the modulation index chart, that is called as the Bessel's function. This Bessel's function are used to directly give how many sidebands will be present in the frequency domain representation of the FM. So these are the modulation indices, this is the carrier signal, and these are the number of sidebands. So if your modulation index is, let's say, 0, then you are having a carrier of 1 only. If your modulation index is 0.25, then you are having a carrier signal of 0.98 and one sideband, that is of 0.12. If your modulation index is 0.5, then you are having a carrier of 0.94 and two sidebands. This will be on both the sides. From right hand side, you will be getting 0.94, 0.24, 0.03. If it is 0.77, then you are having three sidebands on the right side, three sidebands on the left side, and the carrier signal strength will be here in the first column that is given. So this is the Bessel's function, which is used to indicate the number of sidebands from whatever the modulation index that you have calculated by using the readings, that is F2 minus F1 and F2 plus F1. So this is what the Bessel's function that you are going to use for calculation of the number of sidebands. So this is what the, now let us observe the frequency spectrum, that you will be able to see this. So for observing the frequency spectrum, let us just push this FFT button, and you will be able to observe the spectrum here. You have to adjust the scale in order to observe the number of sidebands, and see So, so this is what you are observing, the spectrum. This is the frequency domain representation of frequency modulation. So these are what the spectrum representation of frequency modulation. So whatever the modulation index that you have calculated, based on that you should get the sidebands accordingly. So this complete represents the spectrum of your frequency modulation. So we had seen the frequency modulation signal generation. We had seen the modulation index calculation. We had also seen how to observe the spectrum. So this is the frequency modulation practical we had seen in three parts. I hope every step is clear too. So first, just let's revise it. First, we are generating the carrier signal of high frequency 50 kilohertz. Modulating signal that we are generating of 500 millivolts. Frequency we are keeping it minimum. Then we are applying the modulating signal as input to IC8038, which is generating the frequency modulating signal. At the output of buffer, you will be able to observe the FM modulated signal. For the demodulation, output of frequency modulated signal should be given as input to IC 565 PLL. Before that, you have to set the frequency which is matching the carrier frequency. So PLL had to set the frequency of 50 kilohertz. So at the output of PLL 565, you will be able to observe the distorted version of your modulating signal. This modulating signal you have to give at the input to your low pass filter. So at the output of your low pass filter, you will be able to observe the modulating signal. So this is the complete frequency modulation practical. I hope all the steps are clear to you. Thank you.